Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing moving charge and magnetism. In this lecture we will discuss magnetic dipole moment of a current carrying loop. Of a current carrying loop. Okay. Magnetic dipole moment of a current carrying loop. Also, after completion of this discussion, we will discuss some fundamental numericals on the basis of this theory. Okay. Basic theory and basic numericals. Okay. Magnetic dipole moment of a current carrying loop. Okay. So what is the basic thought behind it? As we have discussed in this chapter, a current carrying loop or a current carrying conductor, simply speaking a current carrying conductor. A current carrying conductor produces magnetic field all around it. A current carrying conductor produces magnetic field all around it. Again, now in this lecture we are discussing magnetic dipole moment of a current carrying loop. Okay, current carrying loop, say this is a current carrying loop. Okay, this is a current carrying loop and current flowing through this loop is up. Let's imagine this is a circular conductor to which a source of EMF is provided. Just think like this, and in this circular loop current I is flowing. I have given current in anti-clockwise order. You may take clockwise order, we will see different cases. So this is a current carrying loop. So we are going to discuss magnetic dipole moment of a current carrying loop. Means this current carrying loop behaves as a magnet. Okay. Current carrying loop behaves as a magnet, and a magnet has magnetic dipole. Okay. Just recall electrostatics. Electric dipole, just have a comparison and everything will be easier. Electric dipole. What is meant by electric dipole? Minus Q. This is plus Q. Okay. Separated by a small distance, very small distance. So to equal and opposite charges separated by very small distance, minus Q and plus Q, equal and opposite in nature, separated by a very small distance, constitute electric dipole, and we have discussed all the concepts behind electric dipole in electrostatics. Okay, polar molecule, non-polar molecule, etc. Okay, then what is electric dipole moment? Electric dipole moment is written as P and it's a vector quantity and its magnitude is product of magnitude of any one of the charge and distance between two charges. Q into 2L. 2L is distance between the charges, and for direction, let's take an unit vector. Then what is direction of electric dipole moment? As you know, direction of electric dipole moment is from minus Q to plus Q. Direction of electric dipole moment is minus Q to plus Q. Okay. Then about magnet or magnetic dipole See, if you consider a very small magnet, we are taking a bar magnet. Let this is south pole and this is north pole. Pole strength of two poles of effect of a given magnet is same. Pole strength of south pole is M and pole strength of north pole is also M. Okay. So this is a bar magnet, a small bar magnet, and where there is south pole there must be north pole. As you know, electric charges can be separated. We have discussed. means positive and negative charges can be separated. We have studied different properties of charge, quantum nature of charge, additive nature of charge. So electric charges can be separated. But magnetic poles can never be separated. Magnetic poles can never be separated. Suppose you just imagine this is a bar magnet. It has a north pole as well as south pole. If you cut this bar magnet into several pieces, even a molecule of a magnetic substance, possesses north polarity and south polarity. Then how can you separate south pole and north pole? So magnetic monopole or single pole doesn't exist. Where there is north pole, there must be south pole. Okay. Here, south pole and north pole are separated by a small distance. Let's consider separation between south pole and north pole is 12. Then we are taking magnetic dipole moment. Magnetic dipole moment of a given magnet, small magnet. Then magnetic dipole moment is capital M. It's also a vector quantity, and the magnitude of magnetic dipole moment is similar as that of electric dipole moment, means product of pole strength, any one of the pole strength, and distance between north pole and south pole. Since it's a vector quantity, I am taking an unit vector which is showing direction of magnetic dipole moment, and direction of magnetic dipole moment is from south pole to north pole. Direction of magnetic dipole moment is from south pole to north pole. Again, as we have discussed in electrostatics, see, suppose this is minus Q and this is plus Q. As we have discussed, electric field lines or lines of force start from positive charge and move towards negative charge. Start from positive charge and move towards negative charge. Like this, you can represent a number of electric lines of forces. Okay. Number of electric lines of forces. So electric lines of force are directed from positive charge to negative charge. Okay. Similarly, magnetic field lines, if this is south pole and this is north pole, then magnetic field lines start from north and move towards south. Start from north and move towards south. Outside the magnet. Outside the magnet. See, if this is a body. Suppose I am taking a small spherical body having minus Q, charge minus Q, and this is a small spherical body having charge plus Q. Then electric field lines or lines of force start from the surface of positively charged body and end on the surface of negatively charged body. So, electric lines of force can never be a closed curve, can't never be like this, can never be a closed curve, but magnetic field lines can be closed curve. See, say this is magnetic field line starting from north and ending at south, but inside the magnet, the direction of magnetic field line is from south to north. So magnetic field lines can be a closed curve. So, if you look outside of the magnet, then magnetic field lines start from north and move towards south. Similarly, in electrostatics, electric lines of force start from positive and move towards negative. So, you may compare north pole with positive charge, north pole with positive charge, and south pole with negative charge. Magnetic field lines from north to south, electric lines of force from positive to negative. So you may compare north pole with positive charge and south pole with negative charge. Okay, then what is the result? Direction of electric dipole moment is from negative, means minus Q to plus Q. Direction of magnetic dipole moment is from south to north, because south pole is comparable to negative charge North pole is comparable to positive charge. Okay. So this is the basic comparison between electric dipole and magnetic dipole. Magnetic dipole moment is product of pole strength and distance between north pole and south pole, and direction of magnetic dipole moment is from south to north. Okay. Then now our heading, magnetic dipole moment of a current carrying loop. It means a current carrying loop. A current carrying loop behaves as a magnet and has magnetic dipole moment. And has magnetic dipole moment. A current carrying loop behaves as a magnet and has magnetic dipole moment as it is observed. Then we will see what is direction of magnetic dipole moment, how can you determine it, we will see all these cases. Okay. So I will erase these parts now, because this is simple comparison between electric dipole and magnetic dipole. Electric dipole moment and magnetic dipole moment. Okay. Suppose this is a current carrying loop. This is a current carrying loop. Again I am representing the same diagram. This is a current carrying loop. Suppose current flowing in anticlockwise order. Then as we have discussed, the current carrying conductor produces magnetic field, and this is current carrying loop, it also produces magnetic field. Then how can we determine the direction of magnetic field? By simply using right hand thumb rule. Okay, by simply using right hand thumb rule. See, these are 4 fingers of right hand and thumb is erect. Then what is the rule? Curl your fingers, means these 4 fingers. Curl these fingers along the direction of flow of current. I am curling like this. Along the direction of flow of current, the erect thumb represents the direction of magnetic field. Okay. Then I am showing you the central line. This is direction of magnetic field. This is direction of magnetic field. Okay. This is direction of magnetic field. Okay. Then at every point of this current carrying loop, you can represent magnetic field. How? See, suppose you are considering this point, then current at this point, direction of current will be tangential. If current is flowing in a curved path and current direction of current at this point is along the tangent, then along the direction of flow of current, keep your finger and turn, keep your thumb and again turn. Then this will represent direction of magnetic field in circular form, and here direction of current will be upward. Again we can determine direction of magnetic field lines around this, as we have represented in previous lectures. If you take current direction upward and here current direction is downward for a straight conductor, then magnetic field lines can be represented in anticlockwise order. This is magnetic field lines, and here magnetic field lines in clockwise order. Okay. So here this is direction of flow of current and this is direction of magnetic field. Okay. Like this, this is direction of magnetic field. Okay. Then as we have discussed, taking a bar magnet, this is north pole, this is south pole, magnetic field lines start from north and enters to south. See, here magnetic field line enters and here magnetic field line moves out. Okay, so obviously at the lower part of the circular loop carrying current will be south polarity, and in upper part there will be north polarity. Magnetic field line enters in south, means field lines, magnetic field lines or magnetic field directed from south to north inside the magnet, and outside the magnet it is from north to south. Okay. So this is south pole, this is north pole, field lines enter here and move away from the upper part. Like this you can represent number of magnetic field lines, like this. Okay. Here current is in anticlockwise order, so we are representing magnetic field. If you take current in clockwise order, then this is direction of current, and curl your fingers in the direction of current, and this will be representation of magnetic field like this. This will be direction of magnetic field, and similarly you can represent a number of field lines passing through it. Okay. And here also you may represent like this, like curling fingers, magnetic field lines, and here magnetic field lines like this. So these are simple representation of magnetic field of a current carrying loop. Okay. Then what we have written, a current carrying loop behaves as a magnet, means it shows south polarity and north polarity. Okay. And if it behaves as a magnet, then it has magnetic dipole moment. Then how to find the expression for magnetic dipole moment? Okay. Now I am erasing it. We will study Biot-Savart's law from coming lectures, and one result I will show here, from which we can derive magnetic dipole moment of a current carrying loop. See, suppose I am showing you a current carrying loop like this. Current carrying loop is like this. So this is axis of circular coil. This is circular conductor carrying current, and this is axis of circular conductor. Okay. I am showing you like this. This is a circular conductor, circular loop carrying current. Okay. This is axis of circular conductor. Let current flowing is R. Number of turns is 1. We may take 100 turn, 1000 turn, 20 turn, 50 turn, whatever may be. Here number of turn is 1. So this is center of the circle, circular coil. Okay. Let radius of the circle is A, and from center at a distance R we need magnetic field on the axis of circular conductor. Magnetic field on the axis of circular conductor. Let I is current flowing in the circular conductor, means coil. Number of turn is 1 and radius is A, and we are finding magnetic field at a distance R from the center of the circular coil, and we will discuss this derivation on the basis of Biot-Savart's law. And at this point, magnetic field is B on axis. So magnetic field on the axis of circular conductor is given as, I am showing you just the formula, and we will derive this formula under Biot-Savart's law. Just see this now. Magnetic field on the axis of circular conductor is given as mu naught n I a square divided by 2 into r square plus a square whole to the power 3 by 2. Since here number of turn is 1, so magnetic field on the axis of circular coil or circular loop is mu naught I a square divided by 2 into r square plus a square to the power 3 by 2. Okay. So here radius is A. So this is formula for magnetic field on the axis of circular loop carrying current I, and number of turn is 1. I am writing this in this form. This will be mu naught. This will be mu naught by 2 into I a square, mu naught by 2 I a square divided by r square plus a square whole to the power 3 by 2. Just see, mu naught divided by 2 into 2 pi. Just multiply 2 pi, and here also we will multiply 2 pi I a square divided by r square plus a square whole to the power 3 by 2. Then what we will get? Magnetic field on the axis of circular coil is given as mu naught by 4 pi, mu naught by 4 pi into 2i, 2i into pi a square divided by r square plus a square whole to the power 3 by 2. So see, radius of the circle is a, then its area. Area is equal to pi a square. Area of circle is pi r square. Here radius is a, so magnetic field on the axis is given as mu naught by 4 pi 2 I pi a square is area. I am writing a divided by r square plus a square whole to the power 3 by 2. Whole to the power 3 by 2. This is expression for magnetic field on the axis of circular conductor. Let's see a condition. If distance from center along the axis, I have taken r. If distance from center along the axis is much more as compared to radius of the circle, then here r is greater than a, so r square is much more as compared to a square, means a square of radius becomes negligible. Then magnetic field on the axis is equal to mu naught by 4 pi into 2ia divided by a square is neglected, then r square to the power 3 by 2. Then magnetic field on the axis is given as mu naught by 4 pi into 2ia divided by r. This is our final output. If distance along the axis is much more as compared to radius of the circle, then formula for magnetic field on the axis is given as mu naught by 4 pi, mu naught by 4 pi into 2ia divided by r. Okay, this is our result. Then a simple comparison we will discuss now. Okay, will I erase this part now? Now simple comparison. Will I erase this part and this part? This is final result. Okay. See, suppose I am taking an electric dipole. This is minus q, this is plus q, this is axial line, this is axial line. We have discussed. So electric field at any point means this is center of dipole at a distance r from center of electric dipole. Here electric field E on axis. If I am considering an ideal electric dipole, then electric field on the axis of electric dipole is given as 1 by 4 pi epsilon naught into 2 k p by r. 2 k p by r cube. Sorry, k I have taken. This is k, constant of proportionality. 2 p by r, where p is a dipole moment. Electric dipole moment is p, and it is constant of proportionality from Coulomb's law in vacuum. So in simpler way, we may write electric field on the axis, magnitude of electric field is k into 2p divided by r cube, and its direction as we have discussed from minus q to plus q. Means parallel to dipole moment. Dipole moment, direction of dipole moment is from minus q to plus q, and direction of electric field on the axis is from minus q to plus q, means parallel to dipole moment. This was, we have discussed this in under electrostatics, means electric field at any point on the axial line. We have got it, and here we have got magnetic field on the axis of circular coil carrying current. Just compare these two equations. Thus compare these two equations. Mu 0 by 4 pi is constant of proportionality in vacuum. Okay. Mu naught by 4 pi. Here K means 1 by 4 pi epsilon 0 is comparable to mu naught by 4 pi. Again 2. R cube. Then here it is electric dipole moment, and here we may take magnetic field on the axis constant mu 0 by 4 pi. 2. In place of P, we may take magnetic dipole moment M divided by R cube. This is final result. And here, in place of magnetic dipole moment M, we have got I into A. Thus, formula for magnetic dipole moment of a current carrying loop. Formula for magnetic dipole moment of a current carrying loop carrying current I and area A is given as magnetic moment is product of current and area of loop. Okay, is it clear? Fine. If we have got magnetic moment, dipole moment of a current carrying loop is I into A. In vector form, we may write magnetic dipole moment is I into area vector. Then what is direction of magnetic dipole moment? Along the direction of area. But we have found here electric field on the axis of electric dipole is from minus Q to plus Q. And here minus Q is comparable to south pole, plus Q is comparable to north pole, and thus see current is flowing like this. See, I am holding the circle like this. In this plane, circular conductor or circular coil is there, and current flowing in this conductor, current flowing in anti-clockwise order. If you show the current carrying loop like this, then this is in anti-clockwise, and here in anti-clockwise order current is flowing, and this is the direction of magnetic dipole moment, means this is direction of area. See, this is current carrying loop, current is in anti-clockwise order, and this is direction of area. See, if you keep circle like this, and in this is anti-clockwise order, just turn this circle, this is anti-clockwise order, then direction of area is perpendicular to plane of coil. Direction of area is perpendicular to plane of coil, and this is also direction of magnetic dipole moment. Direction of magnetic dipole moment is along the direction of area, means from south pole to north. Okay, just imagine field lines are entering and field lines are moving away from the coil, as we have discussed in previous diagrams. Okay, if N is number of turns of coil, then magnetic moment is given as number of turn A into I into A, and this is direction of magnetic dipole moment along the direction of area vector. Okay, this is our final formula. Magnetic dipole moment of a current carrying loop, magnitude of magnetic moment dipole moment is NIA, NIA. Okay, then direction is along the direction of area vector, or from, as I have shown you, this is anti-clockwise order, this is anti-clockwise order, this is direction of area, means on the axis, again it is from south pole to north pole. Okay, this is final formula. Then let's have some numericals, two fundamental numericals and basic numericals. Okay, this is magnetic moment, dipole moment of a current carrying loop. I am discussing some basic numericals, easier numericals, you will find it very easier. Question number 1. A wire of length L carries current R is bent in the form of a circle. calculate magnitude of magnetic dipole moment of the circular. Okay. See, this is where let's consider its length is L and it carries a current, let I. Okay, carries current I. It is bent in the form of a circle. It is bent in the form of a circle. Let this is now direction of flow of current in the circular coil. Let's assume like this. This is direction of current and this is the radius of the circle. Okay. Then what is magnitude of magnetic dipole moment? Ni. Here number of turn is 1. Here n is 1. Then magnetic dipole moment is I into A. Okay. So this may be written as I into, in place of area we can write pi r square. Then total length of wire is bent in the form of a circle, means total length is equal to 2 pi r. This length is, the whole wire is bent in the form of a circle. This total length is equal to circumference of the circle 2 pi r. Then r is equal to L by 2 pi. Then magnetic dipole moment magnitude is pi I into pi r square. In place of r square I can write r square is equal to L square divided by 4 pi square, L square divided by 4 pi square. Okay. And finally, this is our answer, magnitude of magnetic dipole moment, pi cancel square. And final answer is I L square divided by 4. Very simple. Magnetic dipole moment is I L square by 4 pi. Is it clear? Okay. The next question. Question number 2. Will I erase it? Fine. Question number 2. Let's take like this. Question number 2. I am showing you a current carrying loop on a given plane. See, this is origin, this is x-axis, this is y-axis, and this is z-axis. See, this is yz plane. This is yz plane like this. This is z-axis and this is yz plane. Okay. Suppose on yz plane there is a circular current carrying loop. Okay. On yz plane there is a circular current carrying loop. Let current flowing in this loop I is equal to 5 ampere. Current flowing in this loop I is equal to 5 ampere and radius of the circle is 30 centimeter. 30 centimeter. Then it is asked to calculate magnetic dipole moment of the current carrying loop. Current carrying loop means here if the circular coil is placed on a given plane, means here yz plane, we can determine direction also by right hand thumb rule. Then first see what is magnitude of magnetic dipole moment. As we know, magnitude of magnetic dipole moment is Nia and here number of turn is 1. Then current is 5 ampere and area is pi r square and this is equals to 5 pi. Radius is 30 centimeter, means 30 into 10 to the power minus 2 square. This much. Unit is ampere meter square. Okay, I have not written unit of magnetic dipole moment. Current is ampere, area is meter square, and dimensional formula of magnetic dipole moment, meter square means length to the power 2, ampere means current, A to the power 1. Unit dimension you can estimate it very easily, current into area. Okay. Then what we are getting? 5 pi into square of 30 is 900 into 10 to the power minus 4 ampere meter square. Then this is 3500 divided by 10 to the power minus 4, you will get 0.45 pi ampere meter square. 0.45 pi, and you may put here in place of pi 22/7. This is our answer. And what is direction of magnetic dipole moment? What is direction? See, we are considering YZ plane. On this plane, the coil is placed and current flowing in clockwise order. Current in clockwise order. See, here current in clockwise order. If you see, direction is inward, but here the coil is placed here. Current is clockwise, and here if you take current in clockwise order, then direction is along negative x-axis. See, just imagine this is YZ plane and current is flowing in clockwise order. Then this is direction of magnetic dipole moment, means along negative x-axis. So direction you may take minus I cap. Unit vector along negative x-axis, along positive x-axis I cap, and along negative x-axis this is minus I cap. 2 EGMs. Okay. The next question. Next question. I am just erasing this. Question will be same. Question number 3. Again, the coordinate system x-axis, y-axis, z-axis. Suppose this is a rectangular current carrying loop. Rectangular current carrying loop. Rectangular current carrying loop, and current is flowing in this loop 5 ampere. Current flowing in this closed loop is 5 ampere. You may name it O, A, OP, QR. Rectangular loop, current flowing is 5 ampere. Okay. Left, this side is 2 meter and this side is 3 meter. Then we have to find what is direction, magnitude and direction of magnetic dipole moment. So calculate magnetic dipole moment of the current carrying loop as shown in figure. And magnetic dipole moment in this case is Ni, N is 1, current into area. Then first get magnitude, current is 5 ampere and area is 2 meter into 3 meter. So magnetic moment is 6 into 5 means 30 ampere meter square. So what is direction of magnetic dipole moment? 30 ampere meter square. What is direction? See, it is just placed on xy plane. Very easier to determine. Curl your fingers along the direction of flow of current. Along the direction of flow of current means in clockwise order, and this is direction of magnetic dipole moment in clockwise order, and direction is inwards. See, in outward direction positive z axis, and in inward direction negative z axis. Means if you give vector mark, then direction is along negative z axis, means unit vector is minus k cap. Minus k cap. So these are very simple question. Then another question, similar question like this. Okay. Question number 4. Again I am taking xy plane, x-axis, y-axis, and this is z-axis. Suppose it is given a triangle. This is given a triangle. Okay. This side is 5 centimeter. This side is 5 centimeter. And base is let 8 centimeters. P, Q, R. P, Q, R. Let current is flowing in clockwise order. Current in clockwise order, and current flowing means you may take magnitude of current, let 10 ampere. Current flowing in anti-clockwise. Current is flowing in anti-clockwise order, and magnitude of current is 10 ampere. This side 5 centimeter, this side 5 centimeter, and base is 8 centimeter. Then what is magnitude of magnetic dipole moment? Current into area. So this is height perpendicular. See, the total length is 8 centimeter. And this is perpendicular bisector. This is 4 centimeter and this is 4 centimeter. See, PQR. Suppose this midpoint is S Then this is a right angle triangle. Base is 4, hypotenuse is 5. Then perpendicular means this height is 3 centimeter. Square root of 5 square minus 4 square is 3. Then magnitude of magnetic moment is current into area. Area is half base into height. So magnitude of magnetic dipole moment, current is 10 ampere. Half base is 8 and height is 3. Then it will come 5, 40, 120 ampere meter square. 120 ampere meter square, and about direction, current is flowing in anti-clockwise order. Current is flowing in anti-clockwise order, and the coil is on XY plane. Current carrying loop on XY plane. So what is direction? Just curl your finger in anti-clockwise order, and this is direction of current. Means along the direction of positive z axis. Positive z axis. So direction is. Is it easier? Okay. Last question. Okay. Last question. See. Again, the coordinate system. The see. Very easier. This is x axis. This is y axis. And this is z axis. X axis, y axis, z axis, and this is origin. This is origin. Let's consider a current carrying coil is like this, in this form. In this form. Okay. In the form of a parallelogram. In the form of a parallelogram. Let this side is, you may name it OPQR. This is current carrying loop OPQR. Okay. So this side is 20 centimeter. Or you may take both sides same, 20 and 20. Okay, square loop. But it is inclined. It is not on any given plane. Means not on XY plane, not on YZ plane, not on ZX plane. It is like this. It is inclined. Say, this angle you may take 60 degree, 30 degree, 45 degree. Let this angle is 30 degree. And current is flowing in this coil. Current is I. Then magnitude of current here. Magnitude of current, let's take any value, you may take 10 ampere. Then it is again asked what is magnetic dipole moment of this current carrying loop. What is magnetic dipole moment of this current carrying loop? Let's see. Magnetic dipole moment is Ni, and here number of turn is 1, means current into area. We have current 10 ampere. Then how can you calculate area of this coil? How can you calculate area of this coil? See, area is equal to product of these two sides, 20 into 20, 400. 20 into 20, 400. No, we need magnetic moment along the direction of area vector. So area in vector form. Magnitude of area is 20 into 20, 400 centimeter square. Okay, but we have to represent area in vector form. This angle is 30. Then area is equal to let QR into OR into R. So area of rectangle or square, cross product of the sides, area vector. Okay, area vector OR cross R. This is OR. This is the direction of RQ, the same direction, RQ, this direction. Then OR cross RQ, then direction of area will be in outward direction, but perpendicular to this plane of coil. perpendicular to this plane of coil, not perpendicular to any one of the plane xy or yz or zx. So in vector form we are taking like this, then OR. How can you get OR? Thus resolve OR. This is one rectangular component and this is other rectangular component. Okay, then OR may be written as, OR may be written as, see, this side is also 20 centimeter, so this is 20 cos 30 and this is 20 sin 30. This is 20 cos 30 and this is 20 sin 30. Thus OR is equal to, this is in centimeter, I may write is 20 into 10 to the power minus 2 in meter cos 30. Direction is along x axis I cap plus, this is along z axis again in meter 20 into 10 to the power minus 2 sin 30 and direction is k cap. This is expression for OR. Then OR is equal to 20 into 10 to the power minus 2, bring it outside, 20 into 10 to the power minus 2, 20 into 10 to the power minus 2, and here it is cos 30. Cos 30 is root 3 by 2 I cap plus sin 30 is 1 by 2 k. And finally OR is equal to 1 by 2, 1 by 2, bring it common, and finally 1 by 2 into 20 into 10 to the power minus 2 is 10 into 10 to the power minus 2 into root 3 I cap plus k. Okay, this much magnitude in meter square. And now OR is in vector form. Now area vector is OR vector cross RQ vector. In place of OR I am writing 10 into 10 to the power minus 2 into root 3 I cap plus k cap cross RQ. RQ is 20 centimeter, means 20 into 10 to the power minus 2, but direction is along y axis. This direction is along this direction. RQ along y axis means j cap. Again, so area vector is, just bring it outside, 20 into 10 to the power minus 2 j cap. This is in the form of I cap plus k cap. Okay, then 20. Okay. Suppose bring 1 by 2 common and here it is 10. 10 to the power minus 2, bring it common. Then inside bracket 10 root 3 I cap plus 10 k cap. 10 to the power minus 2 is common, cross 20 j cap. Cross 20 j cap. Okay, I have multiplied 10 and 10 to the power minus 2, 10 to the power minus 2 I have brought common. Okay, then area vector is 10 to the power minus 2, it is in meter square now. And you know the rules of cross product in same order. Let's take I cap. This is j cap. This is k cap. I cap cross j cap is k cap. J cap cross k cap is I cap. K cap plus k cap cross I cap is j cap. And in reverse order, j cap cross I cap is minus k cap. I cap cross k cap is minus j cap. You know it. Okay. Now 10 to the power minus 2. First 10 root 3 I cap cross 20 j cap. So it will come 10 root 3 into 20 into I cap cross j cap plus 10 into 20 and in bracket you will take k cap cross j cap. Okay. Now final result for area vector 10 to the power minus 2. I cap cross j cap. See, I cap cross j cap is k cap. I cap cross j cap is k cap. This is 200 root 3 k cap plus 10 into 20 again 200. K cap cross J cap, K cross J in reverse order means this is minus I cap. So this is minus I cap. Am I clear? K cross J, just see it. K cross J, K cross J, I cap cross K cap, K cap cross J cap and area in the form of root 3 I cap plus K cap. Okay. Then 20 into J cap. 20 into J cap. Okay. Let's just calculate it. This is 200. This is also 200. This is I cap minus I cap. Then area vector is 200 into 10 to the power minus 2 inside bracket root 3 K cap minus I cap. This is formula for area vector. Fine. Then what is magnetic dipole moment? Magnetic dipole moment is I cross A. I am doing here. Magnetic dipole moment I. Current is 10 ampere. Area is 200 into 10 to the power minus 2 into root 3 K cap minus I cap. Now calculate. This will be 200 into 10, 2000 into 10 to the power minus 2. Okay. Now calculate it. 10 to the power minus 2, 200, then 20 into root 3 K cap minus I cap ampere meter square. Just review it, check the answer. If calculation is correct, then it is correct. If calculation is correct, then finally it is correct. Area vector, just see again, check area vector. Area vector, we have first calculated OR. OR is 20 cos 30 in meter and 20 sin 30. Cos 30 is root 3 by 2, sin 30 is 1 by 2, 20 into 10 to the power minus 2, bring it common, 1 by 2, 1 by 2, then it is 10 into 10 to the power minus 2, inside bracket it is 3 root 3 I cap plus K cap. Okay. 10 into 10 to the power minus 2 into root 3 I cap plus K cap, then magnetic dipole moment is, area is OR cross RQ in place of OR. This is RQ along J cap. Then 10 to the power minus 2, 10 to the power minus 2. This is 10 root 3 I cap, 10 K cap, and this is 20 J cap. 10 root 3 I cap cross 20 I cap cross J cap. This is correct. Then 10 into 20 K cap cross J cap. This is also correct. 10 to the power minus 2. Then this is 200 root 3 I cap cross J cap is K cap. Then this is 200 K cap cross J cap is minus I cap. And finally 200, bring it common, 200 into 10 to the power minus 2. And inside bracket root 3 K cap minus I cap. Then magnetic dipole moment is I into A in place of area. Directly put this and into 10. This is 10 to the power minus 2, this is 2 into 10, 20 into 3 K cap minus I cap. Okay. Let's check the calculation. Okay. Thank you. Thanks, my children.